Oh, it's on my fuzzy subsets. No, it's none of my fuzzy subsets. You know, I did an experiment with EE505 this summer. I've never done it before in teaching the course. I gave the whole course over PowerPoint. And you'd think everybody would just love to see all the slides on PowerPoint. You know what happened? I got negative feedback and my student ratings went down because everything was on PowerPoint. Because I think there's this tendency of having a talking head. So now I don't know what to do. I don't want to go back to the other way. So what I'm trying to do is to make it a little hybrid sort of situation. We have a little bit of talking head, a little bit of interaction, because I think waving the arms and facial expressions are important too. So we'll see how it goes. So we're still experimenting with the new media. So let's kind of review what we talked about last time. We talked about some of the motivation for fuzzy logic. Let's not look at this yet. We looked about some of the motivation for fuzzy logic. We looked at the blind man and the elephant sort of way of looking at things. There were different ways to look at fuzzy logic, possibility versus probability. We looked at Gödel's theorem, bipolar paradoxes, and maybe the existence of half-truths, and interpreting the paradoxes. Well, you know, not true, not false, kind of halfway in between. That might lead to fuzzy logic. And we also spent some time, and I think it's very important time, to differentiate and distinguish the difference between probability and possibility, between fuzzy set theory and conventional probability. They both are attempting to measure a type of uncertainty. However, the uncertainty that they're trying to measure is much, much different. Fuzzy sets tries to measure uncertainty, and probability is sort of an uncertainty in the future. We then also looked at the motivation of fuzzy logic through interpretation of linguistic statements, that a lot of the terms that we use are linguistic and we don't have them defined precisely, such as far, near, faster, and etc. So we had a way to distinguish between that too. We started into the actual codification of fuzzy systems through the concept of a membership function. A membership function is assigned to a fuzzy linguistic variable to dictate the degree of membership of an element within a set. Conventional Boolean logic says you're either in the set or you're out of the set. Fuzzy logic says, you can be halfway in, halfway out. And so there are certain things that are more into the set than other things. And indeed, most of the fuzzy linguistic variables that we looked at could be interpreted that way. We also saw that non-ordinal measures, such as the beauty of something. Wasn't there a movie called 10? Anybody? Who was that?
Dudley Moore was in that movie.
Demi Moore? Dudley Moore. Okay, Dudley Moore and Bo Derek. Bo Derek, right. And what was the 10 referring to? Attractiveness on a scale of 1 to 10. That was the whole premise of the movie. So actually they were putting forward a fuzzy measure of a non-ordinal quantity, although that wasn't apparent in the movie. Okay, so we looked at the idea of assigning a fuzzy membership function, and then kind of the incredible thing that even though I say someone was running real fast, and you say, yeah, I understand what you mean by that, that your concept of fast and my concept of fast are kind of vague, and in terms of mathematical description are characterized maybe by different fuzzy membership functions, and that we can make these fuzzy membership functions, but again, like the on a scale of 1 to 10, they're going to be heuristic, and maybe we might not agree. However, we'll kind of be in the ballpark, and allows us at least to communicate on these matters. We looked at some of the different fuzzy membership functions. We first of all looked at discrete membership functions, discrete being for example, cities which were far being the fuzzy linguistic variable, cities which are far from Los Angeles, far being the fuzzy linguistic variable again, and we looked at New York and Chicago, and the further away they were, the greater they were into the membership of cities that were far from Los Angeles. So all of that made a lot of sense. We ended up last time looking at continuous fuzzy membership functions, which we said, for example, as is on the overhead here, continuous fuzzy membership functions being numbers which are close to 2. Here we have, ooh, that's a nice pointer. Isn't that nice? pencils. That's my new pointer. We said U sub B, set B. Now the set now is a fuzzy set. It's not a conventional set. It's a fuzzy set because elements have more or less membership in the set, and the set is usually defined by a fuzzy linguistic variable, in this case near. We said that here was a nice membership function, e to the minus x minus 2. This wasn't a good one since it went to infinity, and I haven't changed it yet, but I need to. So here is an example of a fuzzy membership function. And then we began to talk about the concept of subsets. A fuzzy set A is to be a subset if U sub A of x is less than or equal to U sub B. And then we talked about that in terms of tall people and very tall people. And that if you're in the set as a tall person, you're going to be in the set of very tall people, but not as much, because very is a descriptor. And actually went through an argument where we might want to use, at least heuristically, the square of a function to define a new membership function, which was less than or equal to the original membership function, so that the new membership function was actually less and corresponded to a subset. We also said it was important in talking about fuzzy systems, every time we gave forth a proposition, is to compare it back to Boolean or conventional to logic value, because that's kind of a sanity check. We want to make sure whatever propositions we put forth, if we interpret them as a Boolean variable, that it digresses to the conventional Boolean logic definition. And we did that for subsethood. Here's an example of a crisp membership function. They're either 1 or 0. Their membership functions are 1 or 0. There's a crisp set. The number's greater than or equal to 10. So here would be the set of all values of x at x is greater than 10. Its membership function, corresponding to inclusion in the set or exclusion from the set, is 0 up to 10. And because, let's see, there's no inequality here, the value of 10 is outside of the set, and boop, the value of 10 goes right in the set. So that would be an example of a crisp fuzzy membership function. Now we'd like to talk, we have a set theory defined. Now we would like to put logic associated with these sets. What do we do with conventional sets? Well, we combine them in accordance to different logic operations, such as we perform complements. Complement of a Boolean variables when a 0 goes to a 1 or 1 goes to 0. We have the concept of performing union operations or intersection operations. And all of these are very well defined, and I hope very well understood by us in terms of conventional Boolean logic. So we're going to look at some of these for fuzzy logic and see how these concepts generalize. We're going to put forth initially some propositions for fuzzy union and intersection, show that they meet the boundary conditions, and these were the original ones which were actually proposed by Zada in 1965. We'll find out, interestingly, that many of these, in fact, all of Zada's original suggestions for fuzzy union and fuzzy intersection operation are in some ways optimal, even though he didn't maybe know it at the time. It's since been proved that they are. How many have actually read Shannon's original argument for the use of entropy for measuring of information? Anybody? Oh, okay. One person, David. The concept is Shannon, he said, okay, let's see, information. Well, if you do an experiment 2 times, you should get twice the information. And let's see, if you have something which is very, very certain, that doesn't contain very much information. But if you have something very uncertain, that contains a lot of information. And he went through a list of different properties that information had to have and was able to look at those properties and show that the negative log of the probability was the only function in the world that satisfied all of these conditions. It's a very fascinating and monumental contribution to the area of information theory, which indeed Shannon, did I say Zada? Shannon originally defined in his 1948 paper. Actually, Zada could have done this in 65. He could have says, okay, I want a logic operation for a fuzzy and it has to do this, this, and this, and this, and this, and the only function that does this is a minimum operation or a maximum operation. We'll go through these as originally presented by Zada, and then we'll kind of backtrack and show that indeed they are optimal. It's very, very fascinating. So, what are some of the criteria for fuzzy and, or, and complement? They must meet the crisp boundary conditions, in the sense they must revert to the original Boolean logic, if we apply that. And they must have the properties we would expect from typical operations of this sort. For example, if we do an intersection operation, shouldn't it be commutative? Yeah, it should be commutative. It should be associative, in the sense it shouldn't matter the order that we do it in. It should be idempotent, meaning that's a new word, idempotent. Idempotent means if you do it to itself, you get the same thing back. If you do something twice and it's the same as doing it once, it's idempotent. The intersection of A with A is A. That's idempotence for intersection. The union of A with A is A. That's idempotence. Okay? If you have a plane and you perform a projection onto the plane, and you're there as the projection on the plane, and then you project on the plane again, what happens? You don't move because you're already there. That's an idempotent operation. So again, it's the sort of combinations. And monotonic. Monotonicity is something, yeah, thank you. We're closing the door if you can't hear the background problems. Monotonicity is also another concept which we would like to apply, which really isn't as obvious from the Boolean operation, but it will be from the fuzzy operation. For example, if you look at the intersection of A and B, and that's some number, if the membership of A gets bigger and bigger and bigger, what should happen to the intersection of A and B? Well, it should say the same or get bigger, right? So therefore, there is a monotonicity that we would expect from these things also. Now, let's look at an example of fuzzy sets to aggregate. Aggregate, by the way, is a fancy word to put together, to combine in some fashion by an or operation, an and operation, or some sort of thing. And in order to talk about a couple of fuzzy sets, just to talk about pedagogically, let's suppose that we had two sets. A is the set of all values of x, where x, being x as a number, real number, where x is near an integer. And we're going to set B is equal to the set of all real numbers such that this number is close to 2. Now, in both the defining of these fuzzy sets, we have used fuzzy linguistic variables, because here we have the concept of near, here we have the concept of close. Both of those are fuzzy linguistic variables. That's always going to be the characteristic of a fuzzy set. So, what is the membership function for the set A? Again, it's kind of heuristic. You would come up with one, I would come up with one. They would kind of look like the same shape, but they might differ in the details. Here's the one I offer. These are the membership functions for numbers which are close to an integer. I would say maybe a sawtooth, something like this. Here's 0, 1, 2, 3. So if we're right on an integer, 3, 2, or 1, we're 100% into the set. If we're close to the integer, the farther we get away from the integer, the further the membership function decreases. By the way, you'll notice that there's no way that a probability density function could ever have something like this, right? Remember, probability versus possibility? You could never have something like this. It has an infinite area, all sorts of bad problems. Okay, so that would be the membership function for the fuzzy set A. The membership function for the fuzzy set B being all of the numbers which are close to 2, might look like the same thing that we looked at last time. Now what we would like to do is perform a logical combination of these sets. We would like to, for example, do the intersection of A and B. We'd like to do the union of A and B, just like we do for conventional Boolean logic. Zada originally says that a very nice union operation, or the logical OR, is a maximum operation. U of A or B is equal to the maximum of the membership functions. Now this has a nice property in that, first of all, it meets the boundary conditions for the original intersection, if you'll notice. If we have A and B, and then we have A intersect B, you'll notice that we can actually get the union by taking the maximum across the rows, couldn't we? Maximum 0, 0 is this, 1, 1, 1. So if we take the maximum of both of them, certainly it meets the boundary conditions. Kind of an interesting result. Is that the only way that we could actually get this column from these two? No, there's probably other combinations that would meet this boundary condition, but certainly the maximum does. Also, if you look back at your Lukaskovich table of half-truths, where we had the half in there, you'll find that the union operation there for Lukaskovich logic also follows this maximum. So it turns out to meet the crisp boundary conditions. Let's look at some of the other properties here. I lost my pencil. There it is. Okay. It certainly is commutative, isn't it? Right? If you take the maximum of two numbers, yeah, so okay, so that's nice. It's associative, yeah, if you have three numbers, it doesn't matter which pair you take the maximum of. Eventually, you're going to get the right result. It is idempotent. The maximum of 3 and 3 is 3, right? So it's idempotent. And it is monotonic in the sense that if you increase one of these, then this will either stay the same or increase. If you increase one of these, this will either stay the same or increase. So it's monotonically increasing, meaning that it can't have flat spots. So it does have all of these kind of operations that we would associate with the conventional logic. Well, let's look at this example for the problem that we had. Remember the two sets? These were integers which were close. The numbers which are close to integers corresponding by the triangle. And we had also integers or numbers which were close to 2. Given by this Laplacian curve. If we take these two curves, we superimpose them and we run a maximum operation on them, you'll notice that we get this solid line. And this solid line then is the membership function. It's the membership function of numbers which are close to an integer or close to 2. And if you look at this, it makes a lot of sense. It really does, because what you're saying in each case is that the membership function is either associated with the set A or the set B, and you take the biggest one because of that OR operation. You give the benefit of the doubt. An OR is kind of giving the benefit of a doubt sort of operation. So it does make sense, and it makes sense intuitively. Let's look at the intersection operation. Well, if the logical OR is a maximum, then the logical AND can be nothing more than a minimum. And indeed, this works also. It does meet the crisp boundary conditions. If we look at the operation of intersection, you'll notice that the operation of intersection can be obtained by taking the minimum of each row. Right? So it certainly does meet the boundary conditions of Boolean logic. Also, if you were to look at the Lukaskovich, I probably say that name different every time I pronounce it, the Lukaskovich table for the logical AND with the half-truths, you'll also find out that the Lukaskovich table also is satisfied by performing the minimum operations. So let's go down the list. Is it commutative? Yes, indeed it is commutative. Is it associative? Yes, for the same reason maximum is. If you have three numbers, doesn't matter the order that you perform the minimum, they're going to be the same. Is it idempotent? Yes, the minimum of 0.5 and 0.5 is 0.5, right? So it is idempotent, and it is monotonic, in the sense, again, that if you take one of these elements and you increase it, then this is either going to increase or stay the same. So it is monotonic.
I'm sorry, why was it that was an important condition?
Just intuitively, if you think of the linguistics of the problem, you're saying I want a membership of numbers which are close to 2 and which are close to integers. If one of those in that conjunctive statement becomes more dominant, then the entire statement itself must become more dominant or have a bigger membership function, or at least stay the same, right? So if you have two truths linked by an and one of those truths becomes stronger, then the entire statement must get stronger or stay the same. In fact, it's the same thing with an or. If you have two statements linked by an or, and one of those statements becomes more true or has a greater membership, then the composite statement's also going to stay the same or have a larger membership. So that's the monotonicity argument, and it's something which makes sense in terms of our interpretation of the language. Now, let's take a look at the logical operation for our running sets. This again is the set of numbers which are close to an integer, or the set of numbers which are close to 2. I'm sorry, and the set of numbers which are close to 2. So A and B is equal to the minimum. So we're looking at a new set X where X is near to an integer and X is close to 2. And X is close to 2. We maintain that we do this by running a minimum operation across these two membership functions, and in doing so we get something which looks like this. And you can see it does make sense as far as the final membership function being something which demonstrates that we have a number which is near an integer and is close to 2, at least in a rough sense. And all of these are heuristic. We do understand that, but it's nice to see the intuition salved in such cases. And then there's a complement. Anytime you deal with any sort of logic, there's the complement, which takes zeros and ones and makes ones into zeros. And what would that be in terms of fuzzy logic? Well, Zada in his original paper says that the membership function of the complement was equal to 1 minus the membership function. That's kind of interesting. Does that meet the boundary conditions? If we, for example, look at a Boolean operation of numbers greater than 10, here is the membership function for numbers which are greater than 10. What is the membership function for numbers which are not greater than 10? It's equal to 1 minus this, right? Because the numbers not greater than 10 correspond to this. And notice the red curve is equal to 1 minus the black curve. And that's always going to be the case. So it does meet this boundary condition of the Boolean complement, which is something that we would expect. Let's look at it in terms of one of our examples. We had the set of numbers which were near an integer. Well, the complement of that is the set of numbers which are not near integers. And the set of numbers not near integers is obtained by taking this original membership function of the triangle function and subtracting it from 1, giving the solid curve, which is here. And we maintain then that this is a viable membership function for numbers which are not near integers. And yeah, it works. It works. And it certainly meets this conventional way of thinking about thinking about the idea of fuzzy logic, and it also meets the boundary conditions. One has to be very careful in application of this in terms of the linguistic variables. We might talk about the set of tall people and then talk about the set of short people and think the set of short people is the complement to the set of tall people. Okay? Rigorously, we're not doing that. The set of people that are not tall is different than the set of short people. So when we do a complement, it's inserting the word not in there. Don't use the actual English antonym to the word and ascribe the corresponding complement. Rigorously, we are defining the concept of not. It's not near an integer. It's not tall. And we do not use the word short for being not tall. So again, we go through the different concepts. It meets the crisp boundary conditions. Two negatives make a positive. If you do a complement in a Boolean, this is something we would like in a complement. If you take the complement of the complement, what do you want? You want what you started with, right? And certainly the 1 minus meets that. If you take the complement of the complement, you come back from where you started from. Very interesting. It is monotonic in the sense that if you increase this, you decrease this. It's very transparently monotonic. Now, here is one place where fuzzy logic kind of doesn't meet the original concept of Booleans in terms of crisp boundary conditions, in that this fuzzy complement does not meet the law of excluded middle or the law of contradiction. What does that mean? Well, the law of excluded, whoops. Oh, I guess I didn't put it down. Okay. Okay, law of excluded middle. Law of excluded middle. If you have a Boolean operation, and you perform the Boolean operation of A, say A is a Boolean variable, and you intersect A complement, what should you get? You should get the null set, correct? I forget which one this is called. Anybody know? Anybody a logician here? Excluded 56, 57. No, that's either the law of excluded middle or the law of contradiction. I get the two confused. This is the law of contradiction. Then the other one is if you have a union of a set with its complement, what do you usually get? The universal set, right? You get everything. Okay? This is the law of excluded middle. Using min and max and the 1 minus complement, the fuzzy logic operations do not obey this. Let me show you what I mean. Let's look at the law of contradiction. Suppose that we had a fuzzy set A, which was of tall people. A complement would be not tall. If A was tall, it would have a membership function of mu sub A. If not tall, would have a membership function of 1 minus the membership function for A, correct? By what we said. Let's look then at the membership function for A dot A bar. And what did we say that was? The membership function for the intersection operation was the minimum, correct? So we would have the minimum of mu sub A and 1 minus mu sub A. This in general will not be equal to the null set. Because if we were to look at the set of tall people, the membership function goes from the guy 6 inches tall to Andre the Giant, which looks like this. This is the mu sub A. In a similar fashion, mu sub A bar is 1 minus this. So this is the set of people that are not tall. And if we perform a minimum operation on this, you notice what we get. we get this as the membership function for A and A bar. So it isn't equal to 0. Now, can we justify this? Well, it's not tidy in a mathematical sense, but I've come to live with it. Maybe you will too. Yeah, you talk about a person, exactly. That's exactly right. You see a person, you say, are they tall? Are they not tall? Right? They're neither one. They're not tall and they're not tall. So maybe this makes sense in a linguistic sort of interpretation. Maybe it's okay. Maybe it's okay. But in terms of crisp or Boolean logic, we would like to see the law of contradiction not be taken into. We would like to see it work. Let's look at the other one, which is the excluded middle. The excluded middle is the following. If we use the same example of tall and not tall, the membership function for A unioned with its complement is equal to the max of the two. It's equal to the maximum of the two. And if we were to run a maximum operation here, we get this result. And you can see that this is not equal to the universal set. Right? But maybe we could kind of explain and make a rationalization around this the same way that we did around the law of contradiction. Okay. So that's interesting. So it turns out that everything we've looked at thus far has kind of obeyed our original concept of conventional two-valued Boolean logic. And we get to here, and all of a sudden this law of contradiction and law of excluded middle kind of flies in our face. It doesn't, the fuzzy logic does not conform to those conventional laws. But that's okay. That's something we'll live with. What is interesting in the literature, occasionally people seem to rediscover this fact, and they publish it as a big negative comment on fuzzy logic, thinking that they'll dethrone the entire paradigm. And indeed, that's not the case. Fuzzy logic, people know this, you live with it, and you see that you can't get rid of it. And what we'll find out is something very, very interesting. If, as we get on into the next set of lectures, if you use a and an or, because the min and max are not the only things we can use to meet those boundary conditions. If you do another intersection or union operation to force the excluded middle and the contradiction laws to be adhered to, guess what? Something else is violated. It no longer becomes idempotent. So it's kind of like the whack-a-mole sort of game that you play, in that we have all of the moles down except two are kind of sticking up. You ever play whack-a-mole? Where you put in a quarter and the moles come up and you whack them, and when one whacks down, another one pops up. So we got all the moles in the ground except for the law of excluded middle and the law of contradiction, okay? We whack down the law of contradiction, boom, another one pops up over here that we had down before. And you can't get them all down at once. It's really fascinating. It doesn't work with fuzzy logic. Okay, let's look at some of the different properties. And these are really quite remarkable. The min-max fuzzy logic has intersection and distributive, has the intersection operation distributive over the commutative operation. That is, if you take the membership function of A dot B or C, that's the same as a membership function of A or B and A or C. Now, this is exactly the same sort of relationship which you have in Boolean logic, right? It's another one of those boundary conditions, which is kind of interesting. Let's write this down. Mu of A dot B or C is equal to mu of A or B. No, A. Which one did I have? A or B and A or C. Okay. Now, what this means is the following, that this is equal to what? This is equal to the minimum of mu sub A and the maximum of mu sub B and mu sub C. That's what this expression says. You agree with me? Because this is the union operation, which is the max, and this is the minimum operation, which is what is left. If we similarly put here, and we say that this is equal to the minimum of the maximum of mu sub A, mu sub B, and the maximum of mu sub A and mu sub C, we're saying that this is an equality, if this indeed is true. Is it evident to you just by looking at this that they're equalities? It isn't me. It's not readily obvious. However, if you were to play around, and the best way to do this is to look at, I don't know if it's the best, it's the easiest, is to look at three different permutations of A, B, and C, where A is less than these two, A lies between these two, and A is greater than those two, and just show it works for all of those, and you've indeed essentially proved it by looking at all the permutations that are possible in terms of equality on the number line. So indeed, this does turn out to be an equality. Okay, this does turn out to be an equality, even though it is not apparent looking at it. So that's kind of interesting, isn't it? Is it just like in Boolean logic, where you have intersection being commutative over the union operation, we have that same thing using the min-max operation here. And in fact, if you look at the overhead slide, what I've written down is exactly the expression that I've done here, except I've put actual numbers in here as opposed to the membership functions. Now, here's the other thing. This is always that funny Boolean expression where union is commutative over intersection. You've seen this, right? Oh, is that right? Huh? Man, I goofed it up over here, didn't I? Yeah, why don't you say something? Man, I hear making a fool out of myself. Okay, let's go back here. Right? I'm so embarrassed. Okay, this is still the same thing. It's the minimum of, let me just write this down, the max of B and C. And this other one is equal to the maximum of the minimum of A and B. Remember I said those don't look like they're equal to each other? Now we know why. Because they weren't. Okay, here we have the proper expression. And these indeed are equal to each other. Okay? We do the same thing over here, that this is equal to A or B and A or C. This is always the Boolean one that doesn't square with multiplication addition, so it always looks a little bit strange. Similar sort of expression here that we can show is that the maximum of A and the minimum of B and C, which is the expression for this one, is equal to the minimum of the max of A and B and the max of A and C. So it's associative over both variables. It's associative over both variables, which is kind of nice. This expression is exactly the one that I have written down here, that this can be written as this in terms of the mins and maxes, and indeed it does work out, and it's something you should be able to show. Here's one which is really interesting because you wouldn't expect it. I wouldn't expect it. The min and max operations for intersection and union obey De Morgan's laws. Remember De Morgan's laws for Boolean logic? Well, min and max work for it. It's kind of cool. De Morgan's laws says that which one did I have first? B and C, okay. That B and C is equal to B or C, B complement or C complement. This is the conventional Boolean expression for De Morgan's laws. This works for min and max fuzzy logic also. Now, what is the membership function for B and C? It's the minimum of B and C. How do we get the complement? We take the 1 minus there in order to get the complement, right? Is equal to this maximum operation. And what are we doing the max operation on the complement of B? I guess I'm just using the B's. And on C, so we have the 1 minus C using that operation, and indeed this turns out to be an equality also, even though it doesn't appear to be. Again, in all of these, I think we can just use the 3 different permutations of A. Well, I guess here you just have 2 permutations of B and C. And if you show it's equal to them in both, then it will work. In fact, let's do that. Let's assume without loss of generality that B is greater than C. If B is greater than C, what does this turn out to be?
1 minus C.
Yeah, 1 minus C is the maximum of, okay, if B is greater than C, that means that 1 minus B is less than 1 minus C. So if we take the max of these two, that's going to be which one? 1 minus C. Hey, see, it works, okay? And we've actually kind of proven it just by looking at that, okay? Even though it isn't obvious. De Morgan has another law, and it obeys De Morgan's other law too, which is that B plus C is equal to this result. And with fuzzy logic, we're going to call this Zada's fuzzy logic because this was proposed in his original 1965 paper. This does obey Zada's logic. Okay, there's the law of excluded middle, the law of contradiction, a little bit more uniquely defined. We can talk about the Cartesian product of fuzzy sets. By that, where we take 2 fuzzy sets and we combine them using a logic operation into a larger fuzzy set. Let's take, for example, 2 fuzzy sets which are discrete. And one of the fuzzy sets, just to talk about something different, is the fuzzy set U sub G here, which is liquids that taste good. Good being the fuzzy linguistic variable. Okay, I have 0 for swamp water, 0.5 for radish juice, and 0.9 for grape juice. Okay, that's okay. At least it has that monotonic flavor that we need. We know that radish juice tastes better than swamp water, and grape juice tastes better than all 3 of them. So we have this monotonicity outlaid here. And then we're going to use our other set that we used before, which were cities which were far from Los Angeles. Do you remember that? So 0 for Los Angeles, 0.5 for Chicago, 0.8 for New York, and 0.9 for London. Again, the assignment of these variables, these membership functions, is a heuristic undertaking. Now what we're going to do is perform a Cartesian product of these two and look at a new set E. And this new set E is going to be the set of liquids that taste good and cities that are close to LA. It's a stupid combination, but the stupidity of the combination illustrates the power of the generality of the technique, I guess, right? Okay, so let's take a look at this here. We have a following table, and I hope you can see it. I have the cities here, which is Los Angeles, Chicago, New York. No, we need the whole thing in. There's nothing we can do, I'm afraid. New York and London here with a 0.9, and here we have swamp water, radish juice, and grape juice. So, if we were to look, for example, at the membership of Los Angeles and swamp water in the set E. Now, what is the set of E? That's the set of things that liquids that taste good and cities that are close to LA. And I want to do an AND operation on it. AND means minimum, right? So if I want to get the composite membership function between the city of Los Angeles and the swamp juice, I take the minimum of that, which turns out to be 0. Let's take one more interestingly. Chicago and radish juice. Now I have this Cartesian product, and I have an element here, which is Chicago and radish juice, together in one element. Where does that combined element sit in the set of elements of liquids that taste good and cities that are close to LA? Well, it's the minimum of the membership in the cities close to LA, which is 0.5, and radish juice, which also has a 0.5. So therefore, this should be a 0.5. It's a 0.25. I don't know why. Oh, I know what I did. Okay. We multiplied them, which we'll find out is another way of doing intersection as opposed to taking the minimum. Well, think about it. Does it meet the boundary conditions? Let's take a look at the intersection here. A and B. Does it? Minimum works, so does multiplication. There isn't anything magic about the fact that there's different ways that this can be generalized. Usually you have a specific and be generalized in a number of different ways. This is a way that it can be generalized. So in this case, we used it not Zada logic, but we used what's referred to as product sum inferencing, which is, I got the cart a little bit in front of the horse. But anyway, this is the basic idea. If we use the Zada logic, this would have a 0.5 here, right? So you notice not only do we have a sloppiness in the solution of the membership functions, we have a sloppiness in the way we combine them. And we'll talk about that more, maybe not today, but maybe next time. It's really fascinating. And so we have the different results. So what we do is for this Cartesian product is for every one of these elements, we take the product of this element times this element to give us the composite membership function in the Cartesian set, Cartesian product set. Okay? This will actually turn out to be something which is very important when we begin to talk about fuzzy inferencing and the fuzzy inference engine. We've just talked about Zada logic. There's different types of logic. You'll notice that the reason we like the Zada logic is because it had some nice intuitive traits that we would like to have, number one, and including meeting the boundary conditions. But the question arises, is min-max and the definition for complement the only possible things which could generalize from the Boolean into a fuzzy logic? And the answer is there are numerous different ways to generalize it. And let's look at what the criteria for this generalization would be and what some of these other generalizations are. Let's first of all look at the general fuzzy complement. A fuzzy complement. That is, we would like to have a situation where we take a fuzzy variable and we take the complement, tall to not tall. We did this before with the 1 minus. Well, in general, what would we like? We'd like, first of all, to meet the boundary conditions that this is the complement function. If we put a 0 in there, What's the complement of 0? It has to be 1, and the complement of 1 has to be 0. And certainly the complement function of 1 minus x meets this. In other words, we're defining now a complement function as 1 minus a, and what we're saying is that the complement of 0 should be equal to 1, yeah it is, and the complement of 1 should be 0, yeah it is. Okay? But forget this, and let's just look at general cases now of functions that obey this property that are not necessarily this one, that meet these boundary conditions but are not necessarily this one. So these are, if you will, axioms or properties that we would like to see whatever we would have. Plus we have some supplementary properties. In general, we'd like continuity. The concept of the fuzzy system, especially for a fuzzy, continuous fuzzy random variable, is smooth. So we'd like to see the complement kind of be smooth too. We don't want to operate on a set which is just getting an element which is getting more and more of an element of a set and looking at its complement, and one is going smooth but the complement goes radical. We would like, in some sort of step function, we would like to be able to see a smooth operation, yeah.
Is your monotonicity, should that be greater than?
Yeah, it is. It is. This is wrong. Yeah. Thank you. Yeah, this is wrong. So that's the monotonicity. We would like the idea of continuity and involutive. Learning new words, right? Idempotent and involutive are our new 2 words today. Involutive means the complement of the complement is equal to the original result. So these are properties that we would like to have. Well, it does turn out this 1 minus operation proposed by Zada does have this, but there's a bunch of others that do also. One is the Zada complement. The other one is the Seguino class. Hello. By the way, you'll hear the name Seguino quite a bit. Seguino is probably the Japanese engineer most singularly responsible for reduction of fuzzy logic into engineering applications in Japan. He's an incredible theoretician and a very, very applied guy too. He's applied fuzzy logic to a number of things in Japan and started actually the fuzzy logic revolution, even though he isn't given credit for it very much. The Seguino class is a operation that Seguino proposed that has this property, where lambda is any number between -1 and infinity. So in other words, you give me a value of lambda, this is actually a class of complements. This is not a single complement, it's a class of complements. You fix the value of lambda and you have a complement sort of function. You'll notice that for lambda is equal to 0, what do we get? 1 minus a. So the Zada complement is kind of a special case of the Seguino complement. Does the Seguino complement meet the boundary conditions? If you put in a is equal to 0, do you get 1? Yeah. If you put in a is equal to 1, you get 0. Sure. Is it a continuous function? Yeah. Is it involutive? Is that the way you say that? I-N-V-O-L-U-T-I-V-E. See, you don't know, so I can say anything I want to. Is it involutive? In the sense that is the complement operating on the complement of A. What do we want this to be equal to? Want that to be equal to A. Is it apparent just by looking at this function that this indeed is true? The answer is no. It isn't immediately obvious. You have to do a little bit of work. Well, C lambda of A, the Seguino complement, is equal to 1 minus C lambda of A. divided by 1 plus lambda c lambda of a, right? Okay. And now what we have to do is, guess what? 1 minus, what's c lambda of a? That's 1 minus a over 1 plus lambda a. And it's 1 plus lambda, 1 minus a over 1 plus lambda a. Seguino, by the way, is still very viable engineer, still doing some great work. Multiply both sides by a 1 plus lambda a. Let's see what happens here. This 1 eats that 1 up. This lambda a eats that lambda a up. And we're left on the top with a times lambda plus 1. And on the bottom we're left with 1 plus lambda, which is a. Hey, how about that? Pretty slick. It is involutive. So it obeys all of those properties, those intuitive properties that we said that indeed it should have. There's also another example complement. There's numerous of them. In fact, I'm going to make a whole table of them available to you. This one is referred to as the Jaeger class. Ron Jaeger is a fuzzy guy who lives in New York City, and also is a pioneer in fuzzy logic. He's done a lot of really interesting stuff. But he's one of these guys that really loves New York City. He's kind of a Woody Allen sort of guy. He really loves New York City. He was actually offered an endowed chair in Florida. And he said, yeah, I'd like to take it, but you know what? I'd like a week off every month to come home to New York City. And he could not negotiate that, so ended up not taking the chair, and he's still like kind of, huh? It's Icona, I-C-O-N-A, in New York City, and it's not. It's more of a business school than a engineering school. Okay, let's look at the Jaeger class. The Jaeger class says, okay, here is my complement. CWA is equal to 1 minus a to the w raised to the 1 over w, where w goes between 0 and infinity. So just like the Seguino class, the Jaeger class is actually a whole bunch of different complements. You fix w and you get a complement, which is defined. Okay. Well, let's check it out. Does it meet the boundary conditions? If you put in a is equal to 1, do you get out 0? Yep. If you put in a is equal to 0, do you get out 1? Yep. Is it continuous? Yep. What about involutive? That isn't so obvious, is it? That's the one that kind of gets us. In other words, if I take the Jaeger complement of a Jaeger complement, do I get the original function back again? Turns out that indeed I do. I'm not going to go through the math. It's simply plugging and turning the crank a little bit. Also notice something very interesting. If you take this is the W operation. Notice if you take C1 of A, that is, substitute in the specific value of W is equal to 1, what do you get? You get a 1 minus a, which is again the Zada complement, right? So all of these can be thought to be generalizations of the Zada complement in different directions. Yeah.
What does the weighting factor do? Where is that used?
Well, the weighting factor. Let's take a. You know what? I actually have a picture of it, I think. By the way, I told you of my dilemma of having PowerPoint presentations and really not engaging. What I'm going to do is take my notes and I'm going to make GIFs of them and put attachments to the PowerPoint slides so that you have the ability of having everything. That's not done yet, but we'll do that. Could we zoom up on this first one? This is the Seguino class, and this is the Seguino class for different values of lambda. And if you recall, for lambda is equal to 0, this was just the normal zeta complement. And you can see that as lambda becomes less than 0, that the complement begins to bulge out. The fact that it meets the boundary conditions means all of these curves go through one here, go through this point and this point. That meets the boundary curves. The involutive nature is just not apparent. It's kind of cool that it comes out. So as we go negative, the complement begins to bulge. As we go positive, it begins to bulge in the other direction. And in fact, all of the generalizations of the complement kind of look like this. So this is the Seguino class. If we look at the Jaeger class looks very similar in the sense we have, again, for W is equal to 1, the 1 minus operation, which is the zeta complement. And as we increase W greater, it bulges this way. If we make W smaller, it bulges the other way eventually. Okay? Again, the Jaeger class goes through 0 here and here. Questions? Okay, so therefore, if we could zoom out, please. We have the example complements, the zeta complement, and we've talked about the Seguino class and the Jaeger class, both of which the zeta complement is a special class. But both of them meet all of the criteria that we would expect to have from a complement sort of operation. Now, we need to actually address this for different operations also. We're going to do it for the union. We kind of glossed over what sort of properties we'd like to have for the union. Let's be very specific about the properties we would like to have for the union. We would first of all like it to be associated with the boundary conditions. And now we're going to define the union by a two-dimensional function. The complement was a one-dimensional function. The union is a two-dimensional function corresponding to the variables on which it operates, the union of the fuzzy membership functions. So if it meets the boundary conditions, the union of 0 and 0, of course, is 0, and the union of 1 and 1 is 1. So that's a boundary condition we would like the union operation to have. And we found out that the max operation has all of this. We'd like it to be commutative, and that the union of A and B is equal to the union of B and A, obviously. We'd like it to be monotonic. This is what we talked about before. If in the operation of the union, if we increase the membership function of either one of the elements, we would like the union, the composite statement, to either stay the same in truth or to increase in truth. So we have that monotonicity relationship. And we would like it to be associative in the sense that if we perform a union between B and C and then with A, it's the same as A and B and then with C. Certainly that works for the maximum, but are there other cases that obey this property? Supplementary, we would like to be U to be continuous, just as an intuitively nice property, and we would like it to be idempotent in the sense that if we take the union between two exactly similar events, that we generate the same event back again. So let's take a look at these. We have the zeta union, which is the U of A, B is equal to the max of A and B. And we will see also the Jaeger class, and we'll talk about some product inferencing also here. The Jaeger class, by the way, what I plan to do on the slides is after something, I'll put a number here, and I'll put a hyperlink here that if you click on this, you'll get the GIF of the notes that I'm using here to explain that concept. It's really good because it lets me talk to you more in an interactive sort of way, and plus I don't have to do all those equations in PowerPoint, which kill you, you know that. Okay. So general fuzzy unions. Let's talk first of all about the Jaeger class. Ron Jaeger again. The Jaeger class in general satisfies all of the elements except it's not idempotent. Except for the specific case of infinity. Guess what happens if, I should give you a range for W. W goes between 0 and infinity. Guess what U sub infinity of A and B is? This turns out to be the Zeta union. So we've seen, interestingly, that with the complement that we have the original Zeta complement, and we'll find out for all of these that the Zeta union is a special case of the Jaeger union. Again, for the Jaeger union, we would fix the value of W. We would fix the value of W, and we would have a value for the set of unions. This is not apparent, maybe. Is that apparent? This is apparent from that? That a minimum goes to a maximum?
The maximum of A and B.
Huh?
The second one is the maximum of inside the minimum of.
In your first line.
In your first line, the second part of that is the maximum of A and B.
Right. Okay. Okay. Yes. If you're familiar with LN norms, how many have had 510? Okay. So you've seen LN. So this is the L infinity norm, which is the maximum. Okay. Could you prove it? I can. Okay. Let me outline a way that indeed you can prove this, because this comes up in a number of different places in what we're doing. What we're going to do is we'll let C is equal to A to the W plus B to the W times 1 over W to the 1 over W. And then we're going to look at the limit of the log of E, or the log of C, I should say, as W approaches infinity. And of course, that's equal to 1 over W times the log of A to the W plus B to the W. Here we have as W goes to infinity, oh no, I like that. I like that. We have a situation where we can apply L'Hopital's rule. Is that true? Looks more like we have a 0 over infinity situation, don't we? So what's wrong? What do they do? What do they do? What do they do? Okay, this is equal to the limit of this. Right? Oh! Duh. As A and B are both between 0 and 1, right? So if you take a number between 0 and 1, raise it to the infinite power, what do you get? 0, right? And if you take the log of 0, what do you get? Minus infinity. So we do have an infinity over infinity situation, from which we use L'Hopital. Okay? And we take the derivative of the bottom, which is 1, and then the derivative of the top. Well, that's equal to A to the W plus B to the W, and then the derivative of this with respect to W. And the only way to do this is to write this in terms of ease. It's easier to write it that way in order to perform the differentiation. Is that okay? And if we do that, we bring down the log of A here, and then what is left is nothing more than the A to the W. And then we get the log of B times B to the W over A to the W plus B to the W. And this can be written in a very interesting fashion. What I'm going to do is I'm going to break this up. I'm going to break this up into this over this, plus this over this, okay? And if I do so, I obtain the following. Right? If I express this as this, and then take that a to the w downstairs. Okay, once I have this relationship, I can do a few things. First of all, let's look at the case when b is less than a. If b is less than a, what happens to this expression? It goes to 1, doesn't it? Because if b is less than a, this is a number between 0 and 1, right? And this goes to 1, and we're just left with the log of a for the first part. What about the second part? Well, if b is less than a, then this is a number greater than 1, and so this is going to go to infinity, so the entire second term goes to 0, because we reciprocate it. Okay? And I think you can see by the symmetry, this is equal to the log of b under the opposite case. So it is simply equal to the maximum of the log of a and the log of b. And that then was equal to the log of c. So therefore c, if we just raise both sides to the e power, and e to the x is monotonic, so therefore everything's cool. It's monotonic, so therefore if you operate on both sides of an inequality by a strictly increasing function, you maintain the inequality. So the maximum remains the same. So this is c is equal to a and b, which is what we advertised, that this portion went to the maximum. And it isn't apparent by looking at it. If you have had Professor Danborg's class, you'll recognize that yes, this is indeed an L infinity, and an L infinity is defined somewhat like this and corresponds to a maximum. So you might have seen that sort of thing before. Okay, any questions? That's it. You're out before 15:2. By the way, before you go, I will be posting homework on the web by tomorrow evening. It'll be due next Thursday. Thank you.